Welcome to the pre-calculus notes for Unit 1, Lesson 2, Function Families. Today we will be talking about a wide variety of functions, including polynomial and transcendental functions. We will look at how to identify x and y intercepts of a graph and the different types of discontinuity. For each of the function families, we will look at a sample equation, often called the parent function, its graph, and a description of the function. The linear function, with equation y equals x, is often called the identity function. It also contains the constant function and any other non-vertical line. When we look at the graph, what we are going to notice is that we are seeing something which is in fact a line, definitely not a curve. So we're going to write that this is also known as the identity function and can also contain the constant function. When we look at the quadratic family, this is y equals x squared. We note that the graph should look very familiar. It has this nice U shape, and we say that the graph is called a parabola, and that this type of function is commonly used to describe motion in relation to gravity. So anytime that you're talking about something thrown into the air, this is the kind of function that you're going to see. We have the cubic family, which is y equals x cubed. What we're going to notice is a very common graph, which looks like this. It has kind of an N shape, but rounded. Things that we are going to note is that this is a very commonly used graph to discuss the idea of zeros, or to discuss the idea of relative extremes, which we talked about in the last set of notes. So let me write extremes. Next, we have the exponential function, which we are going to write as y equals 2 to the power of x. Note that in this example, or in this function family, x is the power and not the base of an exponent. When we look at the graph of an exponential function, something that is important to note is that the graph will always contain one horizontal asymptote. So we will see that horizontal asymptote. We also want to note that this function is commonly used to show growth and decay in a geometric pattern. Next, we have our logarithmic function. We're going to write this as y equals log base 2 of x. There are other forms of logarithms that we will commonly see, one being natural logarithm, but in this example, we're just going to use the base form of log base 2. We're going to sketch the graph. One of the big things that we are going to notice about the logarithmic function is that there is one vertical asymptote. This might look like it will end up having a horizontal asymptote, but it does not. It only has the vertical asymptote. Next, we have rational functions. The equation for a rational function is y equals 1 divided by x. Important things that we are going to note about a rational function is that it will commonly, not always, but commonly, have more than one piece. This is also called the reciprocal function. Rational functions can have vertical and horizontal asymptotes. Some will have only vertical, some will have only horizontal, some will have neither, some will have both. Next, we have the square root function, which is an example of radical functions. The equation is y equals the square root of x. One example, as I said, of radical functions In the future, we will look at a few others, more specifically the cube root we will also examine. This represents the inverse of the quadratic function. So what you're going to notice is if I look at the graph, which is shown here, if I were to turn it to the side, it's going to look like half of a parabola. So just note that this is related through an inverse relationship to the quadratic function that we already examined. So this is an inverse of the quadratic. Next, we're going to look at some trigonometric functions, which are one example of periodic functions. The one that we're going to graph is y equals sine of x. This graph should be familiar to you. I'm going to do the best I can to graph it. There we go. As I said, this is one example of periodic functions. The big thing to note is that they repeat after a set interval, which is known as the period. Next, we have the absolute value function, y equals the absolute value of x. Most of you probably know what this one looks like because of its V shape. Something to note is that this function describes distance from a point not taking into account direction. Now, while that may not necessarily make sense right now, note that if you were to talk about the difference between distance and displacement, or position and displacement, that is where this really comes into play. So we are going to end up with only positive values outside the symbols. So we calculate whatever's inside, and we say, okay, whatever it was, positive or negative, it's now positive. That does not mean that an absolute value function cannot yield negative values, but this symbol itself will only yield positive values, or 0. The last one we're going to look at is the logistic function. This one's a little more complex. It's y equals 1 over 1 plus e to the negative x. We're not going to use this a whole lot, but it is an important function to note because it is used quite a lot when discussing issues of population. While sometimes you will see exponential functions used to describe population, that is only if the function has non-bounded growth, meaning there are no limiting factors. So the logistic function describes population growth where there are limiting factors. Like, for instance, if there is a limited amount of space or there is limited food, it will cause a reduction in the amount of growth as it reaches that breaking point. So it describes growth with limiting factors. A lot of what we've been doing in these notes is helping us to identify graphs and be able to identify important parts of graphs. Well, when we look at graphs, there's very valuable information that can be found by looking at the x and y intercepts. So an x-intercept identifies where a function crosses the x-axis, and it's written as the point x comma 0, where x is the x value. The y-intercept, likewise, identifies where a function crosses the y-axis and is written as the point 0 comma y. So y-axis and the point 0 comma y, where y is the value on the y-axis where the function crosses. We're going to do two very quick examples about identifying the x and y intercepts. What you will see is that we have two graphs here. There are spaces for us to write the x-intercepts. There are spaces here to write the y-intercepts. So when we're trying to identify the x-intercepts, we are literally going to just follow along the x-axis and identify any places where the graph crosses that axis. So I'm going to follow along the x-axis here. I see that it crosses at 5. So for x-intercepts, I'm going to write that it crosses at 5, 0. Now, there are no other places where this crosses the x-axis, so that is my only x-intercept. When I look at y-intercepts, I'm going to do the same thing, except I'm going to look down the y-axis. I will notice that it crosses here and here. So my y-intercepts will be 0, -1, and 0, -5. So there are two y-intercepts for this graph. Looking at my second graph here, again, I'm going to go through the x-intercept, so I'm just going to follow along the x-axis, and I identify 3 points, -1, 0, 1, 0, and 3, 0. When I'm looking for y-intercepts, again, I am just going along the y-axis, and I notice that it crosses there at the point 0, 3. Our last topic for today is continuity. So first, we have to talk about what do we mean when we say that a graph is continuous. So when we say it's continuous, what we're saying is that all of the points defined by the function are connected with no breaks. So all points connected with no breaks. Now, in a much earlier grade, it probably would have been described to you by saying that you could draw the graph without picking up your pencil, which is what we mean when we say that there are no breaks. So if we're going to be able to define a function and say that it's continuous, we're going to have to look at the graph and determine if there are any points of discontinuity. There are three main types of discontinuity that we're going to examine. The first is the infinite discontinuity, which is also called a vertical asymptote. We know that what we're going to be looking for is we're going to look for places where the function goes to infinity or negative infinity, but not at the ends of the function. So we want to look for where the graph goes to positive infinity or negative infinity, but I definitely wanted to put in that idea that we're not talking about at the end of the function, because we talked about end behavior. We know that sometimes graphs go to positive or negative infinity, but that's not the same thing as a discontinuity. So we're talking about somewhere in the middle of the function. So maybe we'll see something where a graph is going up to positive infinity here and negative infinity on the other side, and we end up with that vertical asymptote. Now, one of the things that you need to be very clear about is it does not have to go to infinity on both sides of the graph. We have seen some other examples where a function will go up to positive infinity like this, and then we'll have an open circle and a line going off to the side. But so at this point, because one side goes to infinity, we say that this is an infinite discontinuity. Secondly, we want to look at point discontinuity, which is also called removable, or we just say that it is a hole in the graph. What we're looking for is anywhere on the graph that there are open circles with no other types of discontinuity. Like we just looked at an example where there's an open circle, but there was an infinite discontinuity here. So we want to look for open circles with no other discontinuity. So we can see this represented in a couple different ways. We might have a function that comes up here, and then there's an open circle, and then it continues. So this is just a hole. Or we might see something kind of similar where there's a hole, and then the graph continues, but there is also a point where that function is defined. Both of these represent point discontinuity because there is an open circle with no other types of discontinuity. The third type that we're going to discuss is a jump discontinuity. This is also called a break. What we're looking for is an x value where the value of y changes. So an x value where y changes. And we don't mean that it changes slightly, we mean there is actually a jump. So just note that this can look two different ways. So I'm going to do an example of both. Our function is going to hit a point. You're going to see an open circle. And then there might be a closed circle where the function continues. So at this value of x, the graph jumped from this y value to this lower y value. Now, I want to be very clear that this uses an open circle and a closed circle, which is very common, but it can also use two open circles. So my graph could come up like this, have an open circle, have a second open circle down here at the bottom, and then, continue onward as the graph. So it may be one open and one closed, or it may be two open. Again, down here at the bottom, there is a space for you to summarize your notes, write down any important points that you want to remember, or write down any questions to ask for the next time that you're in class.